Okay, let's go ahead and get started. First, some announcements. The bad news is that I'm not quite done with the exam yet, but the good news is that I've only got one problem left, so it will be done soon. Although the bad news is that that problem is the B+3 problem, so it's kind of a doozy. But the good news is that on all of the other parts of the exam that I've created, I've been very happy with what I've been seeing so far. So I am optimistic about these exam grades. I am going to grade that problem as soon as I possibly can, hopefully tonight. My goal is to get it done today still. I was hoping to have it done before class, just didn't quite make it there. I'm still hoping to have it done today, so hoping to get it done this evening sometime. And I will make an announcement on Piazza as soon as I have those grades posted. So I'm really, really hoping that it will happen today. Homework 3 is due today as well. So while you guys are working on putting finishing touches on homework 3, I'll be working on putting finishing touches on the exam. And homework 4 is out, which is what we're going to spend a good portion of today talking about. But before we talk about that, I wanted to catch up on the exercises that we left off on previous class. But actually, before we do that, does anybody have any questions about homework 3 or due dates or anything else before we get started? Anything at all? Yes. Yeah, sure. Yes, standard curve. I believe that's on the policies page on Canvas. I'm a little unsure. If it isn't, it definitely should be. I feel like I probably put that up, but I would have to double check and make sure. Yes, and yeah, so it does say that. I reserve the right to curve if necessary. I have been teaching for almost 10 years, and I have not once found it necessary to curve grades. So do with that information whatever you would like. I'm not saying it's impossible, but I am not a big fan of curves. So I will try to avoid them if at all possible. Actually, along those lines, if you're a little worried about your grade, there may be a extra credit opportunity popping up sooner or later, perhaps. So just letting you know that could potentially be an option as well. We'll have a discussion about that in a little bit. Any other questions? Any other questions for me before we get started? All right, so last time we left off with this exercise, and I gave you some time to work on it at the end of class last time, and I'm hoping that between, the time at the end of class and the time that you've had since now and then, that you've got a pretty good grasp on this problem. So I'm not going to give you any additional time. We're just going to dive right in and see how far we can get with it. This is a good little warm-up. Get us in the right frame of mind for thinking about the topics that you're going to be expected to use on homework 4. So we are given this following the schedule that's listed up here on the slide, and first thing we want to do is prove whether or not the schedule is conflict serializable. So what am I going to do to prove that? Prove whether or not it's conflict serializable. What do I need to do? Yeah. We need to make a graph. Yeah, we need to make a graph and see what's up. So how many nodes are going to be in this graph? 3. 1, 2, 3. I'll label this T1. I'll label this T2. I'll label this T3. And then, so we need to add some edges to this graph. What am I looking for in order to add some edges to this graph? What are we taking a look for? Conflicts. So let's start with read-write conflicts. Do we have some read-write conflicts in the schedule? Any read-write conflicts in this schedule? What would I be looking for? Yeah.
R2, or the first
the first task and the last task. So I have a read that occurs before a write on the same data item, but that's not the only thing that matters, right? What's the last piece that matters? Two different transactions, right? So this is an example of a read-write conflict. How do I incorporate that on my graph? How do I draw this edge? From where to where? From T2 to T1, from the earlier operation to the later operation, okay? Cool. Any other read-write conflicts? So I see R2 also reads Y, writes Y, okay? R3 reads Z. Is there a write to Z later on? Yes, there is down here. Here's another one, right? So we'll draw the edge from T3 to T1. Any other ones you guys see? Read-write conflicts? I see a read here on A on transaction 1, and then later on I see a write on A to transaction 2. So what does that tell us to do? T1 to T2, and well, actually, we've already kind of answered our question a little bit, right? For completeness sake, we would continue going, right? So I've looked at the read-write conflicts. I believe that I've found all of them. I would also want to check write conflicts. So look at the write operations and see if any of those conflict. And I believe that there are some that do. For example, this one. Write 3 to write 1, which has us draw the edge that we've already got. So it doesn't add anything. What else do we have? We have, oh, this one right here as well. 2 to 1, which again, we already have that edge on our graph, but it's just been reinforced now. I believe we've found all the conflicts. Does anybody see a conflict that I didn't grab? Yeah.
So what about the third with 3 and then the right 3?
This one here? Which one? So this one writes the same data item, but it's also the same transaction, so that doesn't count. Yeah. Any other ones that I missed? I think I got them all. Pretty sure I got them all. And so this is what our completed graph looks like, and we see there's a cycle here between T2 and T1. So we have definitively proven that this is not conflict serializable. This is not a serializable schedule. And so this second part now, it says, all right, if it's serializable, determine equivalent serial schedule. Well, it's not serializable, so we need to do this part. If it is not serializable, we're going to use the same transactions to create a non-serial schedule that is serializable and then prove that that is serializable. So think about how we could do that, right? Think about how we could do that. We know that the problem is this cycle. We know that the problem is because of the conflicts between T2 and T1, right? So if I want to make a schedule that is serializable, I need to remove one of those edges somehow. I need to get one of those edges out of there so that that cycle goes away. So we need to examine the conflicts that exist between T2 and T1 and see if we can get rid of one of them. See if we can rearrange one of those things. So if I look at, so this one, R2 to W1 is between transaction 2 and transaction 1. This one, though, is going to be tricky to do anything with because it involves the very first and the very last transaction. It's going to be difficult for us to reorder those in such a way that would avoid that conflict. In other words, we'd want to swap the order, right? I want to make it so that this write operation happens before the read operation to get rid of that conflict, right? Because then it switches the direction of the edge in the other in the opposite direction. So it looks like, you know, making the edge from 2 to 1 is going to be kind of tricky to deal with. Let's see if we can find the opposite direction, R1 to R2. So here is a conflict from 1 to 2, which is this guy here, right? This read to this write. So, my first question is, can I just switch the order of those? Is that an okay thing for me to do? Is that an allowable operation? Can I take those two operations and just flip them?
In this case, yes.
In this case, yes. Why? Why is that okay? What would I need to watch out for? What would I need to look out for? Yeah.
Make sure that within each transaction the order of those.
Yeah, so for each transaction, the order has to remain the same. But outside of the transactions, the order really does not have to stay the same, right? So the only thing I'd have to worry about is what comes in between. This is from transaction 3. So if I swap those two, it's not going to affect transaction 1 or transaction 2 in any significant way. And it removes the conflict from T1 to T2. Now, is that the only conflict from T1 to T2? That's sort of the other question to pay attention to, right? And I believe that it is. I believe that it is the only one from T1 to T2, correct? That one's from R2 to R1, 1 to 2, 3 to 1, 2 to 1. So I think that would do it. I think actually the answer here would be to simply swap these two operations. Swap those two operations. What's the graph going to look like if I do that? This edge from 1 to 2 is going to go away. It's going to go away. So this graph is now proof that it is serializable by swapping those two operations. Is it clear how I got to that result? It did require a couple of steps to figure out. I needed to remove one of those two edges because they created a cycle, so I examined the conflicts that caused those edges and tried to see if I could flip them, right? Because if I can reverse the conflict, that means the edge will switch direction. And in this particular case, I was able to do that. Another way to approach this problem could be to start from scratch. You don't have to use this schedule. I could just start from scratch and try to come up with a schedule that meets the criteria. I've seen people attempt that method in the past with success. They've been able to pull it off. The problem with that approach is that I think it's going to take longer because you have to recheck your work. Whereas here, if I just try to modify the existing schedule, I've already got a basis of work to go off of. So it should hopefully be a little bit quicker for me to get to the end result. But whatever approach makes most sense to you is the right one to take. Question?
I presume that this approach depends on an initial schedule.
Depends on yes, it does. In fact, that's something that we talked about on Monday, as a matter of fact, and Wednesday for that matter. Constructing this graph is not something that's often done in practice. And fixing a schedule, also not something that's often done in practice, right? What's done in practice is that I want to generate schedules that I know are good, that I know are okay. And what technique do we use to do that? Generate schedules that I know are going to be serializable. Not just any locking. Strict locking or two-phase locking. Any form of two-phase locking will generate a serializable schedule. It's just what flavor of serializable schedule, what flavor of two-phase locking do you want to use? So strict two-phase locking is what we talked about on Monday as being the most commonly used one. Good. Speaking of which, I've got a couple more review questions. These don't involve drawing anything out, so we can just kind of talk about those as a group, and then we'll hop into the main topic for today, which is going to be homework 4. So we were just talking about two-phase locking. Let's take a look at this question, kind of a review question from last time. Does strict two-phase locking prevent deadlock? So that's the first question, and then depending on your answer to that question, I either want you to explain how it prevents deadlock, or if you don't think that it prevents deadlock, then I want to see an example of a schedule that obeys two-phase locking but also creates deadlock. So let's start with the first part. What do we think the answer to that first part is? Does two-phase locking prevent deadlock? Does two-phase locking prevent deadlock from occurring? What do we think? So if we want to try to answer this question, right, we could think attack this from a couple of angles. We could try to find a counterexample, right? We could try to find an example that meets the second part of this problem. A schedule that obeys two-phase locking but has deadlock in it. That would be proof that it doesn't prevent. If we want to try and answer in the affirmative, right, then we would need to have some way of reasoning about the way two-phase locking works and how that relates to deadlock. So how does two-phase locking work? Let's establish that baseline first. If I'm obeying two-phase locking, what does that mean? What does that mean? Yeah.
Means you must acquire the locks in the next part before releasing the old one.
I have to acquire all of my locks before releasing any of them. So there's two phases, an acquisition phase where I'm grabbing all the locks that I need, and a release phase where I'm letting go of locks. And this does not mention a specific flavor of two-phase locking. So for the purposes of this problem, right, just basic two-phase locking is sufficient to tackle this particular question. So I have a acquisition phase and a release phase. So deadlock then is caused by what? What causes deadlock? Yeah. When two transactions are waiting on each other. So let's think about it this way. Does releasing locks, is that going to cause deadlock? If I'm letting go of my locks, does that cause deadlock? It's really the acquisition phase that is important when it comes to talking about deadlock. So the question is, we don't even have to look very far, right? Can we come up with a schedule that is going to have deadlock during the acquisition phase? And so, we can try it out. We can actually start trying to sketch something up and see what we come up with. Here's the prompt. What kind of locks do you think would be more likely to prevent deadlock? Because we've got two different kinds, right? Or actually more than that. But if we just stick with the basic two kinds of locks, which kind do you think would be more likely to cause deadlock? Perhaps that's a poorly worded question. I don't know. Exclusive locks, right locks? Why? Why are right locks more dangerous when it comes to deadlock? If I only had read locks and I didn't have write locks, would deadlock be a thing? No, because I can have multiple read locks. I can have as many read locks as I want. With write locks, that's not true. So the fact that write locks there can only be one write lock for a data item at a given time is what causes this possibility of deadlock for us. So with that in mind, we can write a schedule then that uses write locks, since we know that write locks are more dangerous than read locks. So let's think of a schedule that might be able to cause deadlock, right? That's sort of the next step. Two transactions, T1 and T2. And actually the classic phase of deadlock looks something like this. I want to write lock X. Over here, I'll write lock Y, right? And then here, actually, I need to make, let me do this over again. We need a schedule. I don't need to see the two transactions. I need to see a schedule. So let me sketch this out in a slightly different way. Transaction 1 is going to write lock X. Transaction 2 is going to write lock Y. And then transaction 1 is going to try and write lock Y. And transaction 2 is going to try and write lock X. This is the shortest possible way I can think of to cause deadlock. Both of them are going to be waiting on the write locks that are held by the other transaction. Right? Does this obey two-phase locking?
Yes.
Yes. I haven't released any locks, right? I've only acquired locks. That's all that I've done. I haven't even actually written any data. So this schedule, it's actually maybe only a partial schedule, but still, this alone is enough to prove that two-phase locking does not prevent deadlock. Does not prevent deadlock. the fact that I am using two-phase locking does not mean that I don't have to worry about deadlock. I still have to worry about deadlock. That is still something that is a potential problem for me. That's something that we spent some time talking about in class on Monday. We talked about various techniques that we can use to deal with deadlock, and that's something that I'm going to ask you to think about on the lab as well. Any questions about this problem? This is the simplest way that I know to answer it. Yes?
So how can the third step require the lock go live to lock happen?
It can't. That's the problem. That's why deadlock occurs. It can't. That's the entire issue.
So deadlock can happen before the transaction.
Actually, so this is a good question. In this case, I would argue that the transactions have already begun. The process of acquiring the locks occurs during the transaction. And so it's important, I think, to kind of think of how this might work. How does a schedule get generated in practice, right? A user submits a transaction. So as a database programmer, or maybe I'm not even a database programmer, maybe I'm just somebody trying to access your website, right? I perform some operation that needs to access the database. That's going to get submitted as a transaction. When I submit that transaction, there is no concept of locking in there whatsoever, right? As a database programmer, I don't have any control actually over when the locks get acquired or released. The database will take in that transaction. The database then will apply the two-phase locking technique by inserting lock acquisition statements and lock release statements into the transaction when it's appropriate to do so. So I can see when the writes are supposed to take place. The database will then just insert the appropriate locks before those operations take place, and the appropriate release statements after those operations take place. So from our perspective, this is actually outside of our control as database programmers. But since in this class we're actually writing the database server itself, we get to implement this and be aware of these kinds of problems and decide how to deal with them, which is what I'm asking you to do on Lab 4. There is one two-phase locking scheme that we talked about that does expect some of the work to happen outside of a transaction. What scheme is that? It's one that we talked about. Let's see. The two-phase locking scheme that I'm referring to rhymes with suburbative. I don't know. Conservative. Conservative two-phase locking says you need to acquire all locks before the transaction begins. So it's a subtle distinction, right? I'm making the claim that for strict two-phase locking, acquiring the locks happens within the transaction. Conservative two-phase locking says I'm acquiring those outside of the transaction, before the transaction begins. That subtle change actually has a significant effect, though, on the execution, because if I am acquiring locks within the transaction, there's a chance that that transaction is going to have to abort, possibly due to deadlock. Conservative two-phase locking actually greatly reduces the risk of deadlock, because if I can't acquire these locks, I'm not even going to start the transaction. It's trying to avoid those transactions being aborted due to reasons such as deadlock. Yes?
If you have conservative two-phase locking, where you are ensuring that all locks are a grouped operation, doesn't that completely eliminate deadlock?
So the lock acquisition has to happen somewhere, right? So it's happening outside of the transactions now, which kind of is sort of a no man's land for us in a lot of ways, since we're mostly concerned about what happens within the transaction itself. It's still entirely possible that two transactions, or that I need to acquire a set of locks for two different transactions that are conflicting with each other, even if those lock acquisitions are happening outside of the transactions themselves. That's still possible, right? But I think what you're more likely to see with conservative two-phase locking is that if I go to acquire that lock and it's not available, I'm not going to wait. I'm just going to give up and try again later. So in that sense, yeah, it does do a very good job of avoiding deadlock from occurring.
Wait, so it's the between described and deadlock not happening at all.
And deadlock not happening at all? Well, conservative two-phase locking, the whole reason that it exists is actually to avoid deadlock. That's the reason why conservative two-phase locking exists. There's a penalty, though. There's a price.
Okay, so deadlock doesn't have anything to do with whether or not the transaction is actually started.
I would say that the effect of deadlock is different depending on whether it occurs inside or outside of a transaction. I mean, deadlock is not isolated only to database management systems. Deadlock, if you take any parallel programming course, you're going to run into deadlock, right? So it's not a situation that's just unique to transactions. It's a problem that occurs in many different contexts.
Deadlock doesn't just mean that if you started the transaction and you can't acquire a lock, it means like terminate the transaction or whatever. Deadlock can also mean, like for example, here in the case that if you can't get the locks to start
Can't get the locks to start the transaction. You could call that deadlock. I think most people would call that a failure to launch even, right? Like, I think we're diving a little bit into semantics at this point. I'm not necessarily too concerned with the differences between those, more the effects of the different types of two-phase locking. That's the primary takeaway that I hope we're getting out of this conversation. I do think that it's important, though, to understand that conservative two-phase locking does come with a price, which is you're going to be very restricted as to when a transaction can start. The transactions may end up being a lot more serial than they would be if I allow them to acquire locks during the transaction itself. Which actually brings us to the final question that we'll talk about, and then we'll talk about homework 4. Will basic two-phase locking lead to better performance than strict two-phase locking in the general case? And so before we can answer this question, we need to make sure we understand the difference between the two. Basic two-phase locking is what we've been talking about, right? Acquire the locks before I release any locks. If I'm doing strict two-phase locking, what's the variation? What's that variation telling us to do? Yeah.
Acquire all locks before operation.
Acquire all locks before an operation is made.
Oh, I'm sorry, that's the wrong one.
Yeah. That sounds more like conservative to me, yeah. Strict two-phase locking is telling us to do what? Yeah. I hold on to all of my write locks until the transaction is over. And the reason for that is to avoid some of the problems that can occur, right? I don't want other transactions to read data that I've modified if there's still a possibility that I might abort and roll that data back, because that can lead to some problems, some computational problems, some correctness problems. So strict two-phase locking tries to avoid the situation where we're reading uncommitted data. If I hold on to the lock the whole time, I know that nobody else is going to be able to see that until the transaction's finished. Yeah.
In strict two-phase locking, could you release after the last write up? Could you release all write locks after the last write operation?
The strict definition says actually at the end of the transaction. So after everything else is already over. Yep. That's the true interpretation of the rule. There actually are other slightly different variations on that rule. And it's also important to note, too, that it doesn't make that same stipulation for read locks, right? So I can let go of my read locks whenever I'm done with them. That is okay. That is perfectly acceptable under the strict two-phase locking paradigm. The only thing that it says we have to do is hold on to write locks until the transaction is ending. So at the end of every two-phase locking schedule, I would expect to see a whole bunch of write locks being released. And so now that we understand the difference between the two, we can try to address this question, right? Will basic two-phase locking lead to better performance than strict two-phase locking? What do we think? Yes or no? What's going to give us better performance? Anybody have any ideas? It's a good rule of thumb here that can help us answer this question. So really, what this question is truly asking us, right, is will holding on to locks for a longer period of time help performance or hurt performance? That's the true essence of this question, right? Because strict two-phase locking says you have to hold on to these locks, whereas basic two-phase locking says, whenever you're done with them, go ahead and get rid of them. So the real essence of this is, if I hold on to those locks, is that going to help my performance or hurt my performance? Or not change anything? What do we think? Is holding on to locks a good thing, a bad thing? Yeah.
My intuition is it does a little of both, because if you release the locks earlier, more operations can happen currently, but you also run the risk of more operations failing, which could have
Run the risk of more options failing.
more transactions.
Your first point I 100% agree with, right? If I let go of locks sooner, that means other transactions can come in and grab that data. The longer I hold on to locks, the less concurrency I'm going to have. The more serial things are going to look, right? So I think that's a big point in favor of strict phase, two-phase locking, slowing things down. Your second point, though, of causing more failures, I think like a transaction doesn't know if the data is correct or not. It's just blindly following your instructions. Maybe that's not exactly what the point you were trying to make, though.
I was referring to the possibility of, and maybe I'm misunderstanding something, but that if you do basic two-phase locking, you run the risk of releasing a write lock, and then the transaction rolls back, and something else is write bad data.
Oh, the transaction rolls back. I actually think the odds of that happening are less with strict two-phase locking because of the fact that the write locks are only being released at the end.
Right. So sorry. So I'm saying with basic locking, the chance of rollback and bad data increases.
I see.
Which is problematic. And
Yes.
the increased concurrency.
I don't think the odds of a transaction failing necessarily go up due to the lock behavior, though. That's the point that I think maybe I do agree with you that the odds of having incorrect data in your database go up.
Yeah.
That I agree with, but I don't necessarily agree that more transactions are going to fail or be rolled back due to the lock behavior. In which case, from a strictly performance perspective, right? If what we're asking about is performance, then I think signs are pointing to basic two-phase locking being faster than strict two-phase locking. And like most things in life, right, this is a trade-off. This is a classic trade-off. We are sacrificing performance. Strict two-phase locking sacrifices performance for the sake of what exactly? What am I getting in return? Hopefully better looking data, more correctness with my data. That's the trade-off we're making. So to the official answer to this question is yes, basic two-phase locking generally will lead to better performance than strict two-phase locking. Yes. All right. Any questions? Thanks for having this conversation. I think you've been asking some great questions, making some great points so far. Any questions before we switch over and talk about homework 4 for the rest of the time? Yes? Can only have one write lock on a data item at a particular point in time. So one transaction can have many write locks, that is true, but they all have to be on different pieces of data, different rows, different tables, right? So the way to interpret this schedule is that transaction 1 wants to modify X, and transaction 1 also wants to modify Y. Transaction 2 wants to modify Y, and transaction 2 also wants to modify X. The fact that we can't have multiple write locks is what creates deadlock here. That's a problem. This schedule is a problem. This is not a good situation to be in. This is a bad situation. We have deadlock because of the fact that only one of those write locks can exist. So transaction 1 would acquire this write lock, transaction 2 would acquire this write lock. When transaction 1 tries to acquire the write lock on Y, it would not be able to do so, and it would wait. And when transaction 2 tries to acquire the write lock on X, it would not be able to do so, and it would also wait. So they would be waiting on each other. But since they're both not progressing, they both aren't moving forward, they're waiting, deadlock has been achieved. Any other questions? Yes?
I probably can you put a write lock on a data item and something else with a read lock on?
No, you cannot. No, I can have multiple copies of read locks, but when I say write locks are exclusive, that, you know, very, very much literal in the sense that that can be the only lock on that piece of data. Yep. If something is locked with a write lock, you know that is the only lock that exists on that piece of data. Yep. Great questions. Anything else we can chat about before we look at the homework? Okay, so I've said it a couple times. Hopefully you have come to the realization that homework 4 is directly related to locking. That's what we're going to be working with on homework 4. So let's pull up homework 4 and take a peek what we've got going on there. It's due a little over 2 weeks from now, so you've got a big chunk of time. I do want to say, actually, right off the bat, I know homework 3 is a beast. Like, I am fully aware of that. Homework 4 is not. Homework 4 is not a massive assignment. It's much more reasonable in scope. I think you guys have earned it after getting through homework 3. So hopefully homework 4 will not be as much of a challenge for you. It's certainly not intended to be as much of a challenge as constructing B+ trees. So homework 4, I'm asking you to implement locking, but one thing that we actually need to help us with this situation is something that we haven't discussed before now. We're going to talk about it today, though. We need a concept of a buffer pool. So earlier on in the semester, we spent a lot of time talking about the organization of data in heap files and heap pages, right? A buffer pool you can think of as just a cache for heap pages. It's a place for me to keep the pages in memory that I am currently working with. So if I have a bunch of transactions performing some operations, they're going to require access to those heap pages. Where are those heap pages going to be stored? They're going to be stored in the buffer pool. It's important for this buffer pool to exist because we need, if we're going to implement locking, I need every single transaction to go through the same entry points to acquire the data that it needs so that we can check to make sure that it has the locks that they need to perform whatever operations they're trying to perform. So that is kind of another role that the buffer pool is playing. It's sort of the lock manager as well, right? It's in charge of making sure that transactions have the locks that they need. And if they don't, the buffer pool will try to acquire those locks, right? We'll try to grab those locks for the transactions so that they can perform their operations. So most of the work that you're doing in this lab is going to be in the buffer pool file. We'll take a look at that file in just a little bit. I do want to point out before we begin that you've probably already noticed that based on my explanation that this does rely on heap files and heap pages. So you do need a functional version of homework 1 to be able to successfully perform this lab. If you think that's going to be a problem for you, if you struggle on homework 1, try to fix it up. And if you need help with that, come talk to me. We can have a conversation about that if you think that's going to be an issue for you. One other thing that I also would like to mention is that it's certainly entirely possible, in fact, perhaps even recommended, that you go back and consider modifying some of the work that you did on homework 1, the heap file and heap page classes in particular, to accommodate the locks that I'm asking you to implement on this particular assignment. So just because you finished homework 1 up and everything's working doesn't mean that it can't be improved. go back and consider updating those files if it will help you complete this assignment. Okay, so the main amount of work is going to be in buffer pool. Buffer pool, I can go ahead and pull up the code for buffer pool. Oh, I already have it? No, that's not the right file. Here we go, buffer pool. I've already got it. All right. Yeah, here's the code for buffer pool. I provided actually all the methods that you are being asked to complete, as well as descriptions of those methods, but we can give a brief rundown of those now. And so the constructor tells you how many pages the buffer pool can store, right? The default being 50, so I can have 50 pages in memory at any given point in time. In practice, we would adjust how many pages can fit based on how much memory we have available to us. 50 is a small enough number to work with that should not strain anybody's computer too much, hopefully. This method right here, the very first one after the constructor, is a very important one. Get page is a very, very important method. And if we look at the parameters to get page, we can see that I've got some various values here. TID is the transaction ID. So what transaction is making this request? Table ID is the table that I'm trying to acquire the page from. Page ID is the ID of the page that I'm trying to acquire. Okay? And then the permissions are what kinds of operations I intend to perform on that page. Am I planning to read the data on that page? Am I planning to write the data on that page? Those are the options. There's a very small permissions class over here for read and read-write permissions. Okay, and so get page is the entry point now. If a transaction wants to read any data or write any data, they have to go through this method first in the buffer pool. First thing the buffer pool is going to do is say, all right, you want this page from this table. Do you have the ability to acquire it? Do you have the locks necessary to perform a read on that page or to perform a write on that page? That's the first thing it'll do. If it does, if you have the locks, if the transaction has the locks, then everybody's happy, right? Give them the page and move on with your day. If you do not, then it will try to acquire those locks for you. And so one of the first things that you're going to have to do is decide on a structure to track what locks currently exist. What locks are currently outstanding in the database. Who has what? So think about what information you'll need to track, and actually be aware that the information that you need to track is going to be different for read locks versus write locks, correct? I can have multiple read locks on the same item, but I can only have one write lock on a particular item. So that's going to potentially change the way that those locks are being tracked and the data structures that you use to track those locks. That's a decision that you're going to have to make pretty early on. All right. So get page is now how transactions interact with the database to acquire pages. That's where the locking is going to come into play. Once a transaction is finished with the page, it's going to actually release page is probably not the preferred way to, well, let me be careful about that. Releasing a page will remove any locks. That a transaction has on a particular page, right? But that should really only happen at a particular point in time, you know, specifically when we get down here, when the transaction is complete. When the transaction is complete. I would expect that transaction to release all of its locks as part of the completion phase, as part of the commit phase of the transaction. So there's definitely some interaction there between a transaction completing and releasing the pages. But along those same lines, there is actually two ways that transactions can finish. One is they can commit, they can finish successfully. The other is there can be an error, they can abort. We can abort a transaction. And when we abort a transaction, that means that we then have to undo any changes that may have been made to its data.
So something that you're going to have to consider, something that you're also going to have to think about on this lab is how can I track what pieces of information a particular transaction has changed in the case that a transaction aborts and I have to undo those changes. It's actually not that difficult when you consider that a permanent change is made by writing the data back to the file on disk. So a simple way of aborting a transaction would be to not write the data back, right? Just throw it out, just chuck it. But you still need to have some way of tracking whether that page has been modified or not, so that you know what data to remove, perhaps. All right. Adding a tuple, inserting a tuple is a write operation, right? So make sure that the transaction has the appropriate lock that it needs. Deleting a tuple is also a write operation. Make sure it's got the appropriate permissions that it needs. Flushing a page. Whoops, actually this comment is in the wrong place. Sorry about that. I will update that and switch it up. Sorry about that. Flushing a page takes a page that has been modified and writes it back to disk. So if a transaction has made an insertion or a deletion to a page, you can use this method then to take that page and write it back to disk. This may rely on some of the methods that you wrote in homework 1. That's totally fine, totally expected. And then last but certainly not least is evict page. So consider that this buffer pool has a certain number of slots. There's only 50 pages that it can store. So what happens if they're all full and then another transaction comes and says, I want a page? We now have a problem, right? The buffer pool is full. I want to load one more page. So what do? I'm going to try and find a page and kick it out. I'm going to try and find a page and toss it. But you need to be careful. You can't just pick any page and throw it out. You need to pick a page to remove that is not currently being used by a transaction. It's not currently being operated on by a particular transaction. The lab write-up goes into a lot more detail about how evict page should work and how you can detect what pages are being used by transactions or not and make the decision to evict the proper page. That's it. I know I say that's it like it's very simple and straightforward. There's not a lot of methods here, but there is a significant amount of conceptual work that you'll need to do, especially with those data structures that track locks. That is so crucial. And speaking from experience, if you get that part wrong, it's going to be a longer lab for you. So please spend some time thinking about that first. Don't just try and slap some code up there and pray that it works. Like, take some time, sit down, sketch it out on a sheet of paper, think very carefully about what data structures you want to use to track your locks, because that decision will hopefully make your life a lot easier if you put some thought into it and get it right. Yeah, and then there was a couple other things that I wanted to mention, but I'm kind of blanking on right now. What's that other thing that I wanted to say? Shoot. Oh yeah, notice that actually, while I certainly could have asked you to do this, there's no transaction object here, right? There's no concept of a transaction object. I think you certainly could create a transaction object. I don't think that it's necessary to perform the tasks that are being asked of you on this lab. A transaction exists mostly via its ID number, right? So with every operation that can be performed, we pass along the transaction ID number, and that's what we use to track the various transactions. Also notice that I'm not asking you to create schedules here, right? I'm simply asking you to perform whatever tasks the transactions are being requested. So in that sense, you can think of this part of the database as executing on an already predetermined schedule, right? You don't have to worry about the two-phase locking so much. You can assume that what is happening, what's being passed to you, is already going to follow the proper two-phase locking protocols. Or actually, you're enforcing the two-phase locking by acquiring the locks and releasing the locks in particular situations. And then last but certainly not least, actually a couple things, and then we'll talk about testing like we usually do. Deadlock. We spent a lot of time talking about deadlock today. Deadlock's a possibility here too. Deadlock is a possibility here as well. And so, as I mentioned on Monday, you're going to have to do something about that. You're going to have to implement one of the deadlock techniques that we talked about on Monday. Here is where things get a little, I don't know how to describe it. For deadlock to occur, it really requires a degree of concurrency, right? That's not 100% true. Deadlock can occur even with serial things occurring, but this homework assignment is screaming for concurrency. We've been talking about concurrency a lot. We've been talking about parallel a lot. This homework assignment is screaming for concurrency. I actually am not requiring you to deal with concurrency on this assignment. I really want to, believe me, I do. But past experience has shown that the amount of people who know how to do parallel programming is too variable for me to actually require that on this assignment. It was a bad time for everybody when I tried to do that. So I'm acknowledging that fact, right? That the parallel programming piece should exist. But the prerequisites for this course actually do not require any parallel programming knowledge, so I think it's unfair of me to require that of you on this particular assignment. However, if parallel programming is something that you do know how to do or something that you're interested in doing, I certainly would be open to having a conversation with you about how to make this a more concurrent implementation, and perhaps even be willing to give you some extra credit for doing that. So if that is something that is of interest to you, come chat with me. I definitely want a heads up. Don't just like do it and then expect that I'm going to give you all the points. Come chat with me first. Or send me an email, something. Just give me some kind of heads up, right, that you're interested in this, so that I can make sure that we're all on the same page. I'm definitely 100% open to the idea. If parallel programming is not your thing, if you don't like it or you don't know how to do it, don't worry about it. You can do everything in serial. That's totally fine. You'll get full credit. No problems there. But this homework assignment really, I think, is a lot more interesting with the parallel stuff involved. So give it some thought. Think about it, and let me know if you want to have that conversation. Before we switch over to unit tests, does anybody have any questions about sort of the basics that we've gone over so far about the assignment? We got about 25 minutes left, which we're going to use to talk about unit testing. So let's switch over and do that. Like you've seen on the prior assignments, I've given you some examples of unit tests. And this question's actually come up a couple times, so let me make this clear right now. The transaction tests are purely examples. You will not be graded off these tests at all, none. You will be graded off of the unit tests that you write and that you submit to me and that I then give back to you. Those are the ones that you're graded on. These are purely for example purposes. They may or may not line up with the tests that you are in fact given later on. But let's take a look at a couple of examples here, right? I see a test called test release locks, and we can actually think through this real quick and try and decipher what this test is trying to do. First, I see that I'm acquiring a page, acquiring write permissions on that page. Transaction number 0 is acquiring page number 0 from this table, and it wants to read it. And then transaction 0 acquires page 0 and says it wants to write. What is this an example of? I had a read lock, and then I say, actually, I want a write lock. What's that an example of? That's an upgrade or a conversion. I'm converting my read lock from a write lock. Is that okay? Am I allowed to do that? Yeah, actually, yes. We talked about it. Yes, I can convert my read lock to a write lock. And vice versa. That's also allowed. I can convert my write lock to a read lock if I want to. That's allowed. And then it says, all right, this transaction is over. Transaction 0 is completed. The fact that I see a true here means that it completed successfully, right? So after this point, I would expect these locks to be released. I would expect those locks to have been let go. They no longer exist. The transaction's over. Should have let go of those locks. Then transaction 1 comes along and tries to acquire similar locks, right? Tries to acquire a right lock. It should be able to do so. This is not an example of deadlock. This should be fine because the locks should have been released. Should have been released here. So if this test freezes up, if deadlock occurs, that means the locks were not properly released. The test will actually potentially go on forever. Maybe not the best way to write a test, now that I think about it. Oh well, you guys can write better ones, I'm sure of it. So release the locks and then try to acquire more locks. This should work because the lock should have been released. Here's an example that tries to insert a tuple, and then after the transaction is completed, it goes and it checks to see if that tuple actually made it. Did that tuple actually make it? If I were to check to see before the transaction was complete, would I see that tuple or not? I grab a page, I insert a tuple to that page. I check to see if the tuple is in the file. Would I see it? No, I don't see that tuple until that transaction is committed. A transaction commit is what makes that operation permanent. It's very, very important. Very, 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 very important. Other transactions would not be able to see this tuple that was inserted until the transaction is declared that it is complete. So it puts the tuple in, completes the transaction, and then checks to make sure that the tuple made it. And then for aborting, puts the tuple in, and this time it says complete and says false. That should undo the insertion that takes place, right? It never actually happened. We aborted, never actually happened. And then checks to make sure that that tuple did not actually make it to the file. So I've only given you 3 tests. That's not very many tests. I expect actually to see a lot more tests. And like last time, I think it's a good idea to consider what tests could be written. So before you leave here today, I want to give you some ideas on what unit tests you could write and submit for this particular assignment, because I'm expecting you to submit a couple of unit tests to me by Friday. So a good way to go about this is to open up the buffer pool file and examine these methods. Ideally, I would like to see some unit tests for all of these methods, for all of them. And so what I want you to do for the next 5 or 10 minutes is to grab a copy of buffer pool or consider the important methods from buffer pool, getting pages, inserting tuples, deleting tuples, committing transactions, and think about what would need to be tested for those particular methods. Write down a few ideas, talk to your neighbors, write down a few ideas. I'm going to give you a few minutes to do this, and then we will write down some ideas together as a group so that you have some ideas of what you can do when you leave here today. All right, I'll be around if you have any questions, okay?
Not that my
Well, if I'm acquiring, that's not I know that I don't use access. I want
so it's not fair. That's the whole point. On these areas.
providing
And
an
then it
issue.
shows like on those it shows like the value of the job. So it's kind of like the value of each element. It's very helpful. I will.
So I can't do this.
I really want the whole lot.
That's very cool.
Sign first, I'll be right back.
The problem with that is that I'm not working on Saturday. And you brought that up. I guess I could technically give you an extra day, but you wouldn't actually get the test back until the following week.
So you have to do that 12 for that afternoon.
That's right. Get it back to you by the end of the day. That's the plan.
I'll be right with you. What's up? I'll get to it as soon as I can. Yeah. It's not a huge priority for me because I'm hoping that the same class is going to do this, but I will get to it eventually. Hopefully. Videos are not a huge priority to me. They're not, they're a thing that I certainly try to do, but they're way down on my list of priorities. I would much rather people come to class and interact with us. Yeah, I understand. What's up?
I will do that.
So they're, yeah, well, so these are just examples of tests. Actually, they look very similar to examples that we've seen on Kingston. With a few slight modifications. There's a lot of stuff to do with this. I'm just looking for ideas. We're talking just very conceptually what things should be tested. So we're actually about to start to talk about it in a couple of minutes. Okay, we got about 10 minutes left. Let's talk about some ideas of things to test so that when you walk out here today, you've got some thoughts on what unit tests you can potentially try to write. This is a homework assignment that is very much geared around locking, right? Very much geared around locking. So who's got some ideas for me of, it doesn't have to be complicated, just general, very basic things that we should be writing tests for. Somebody got some ideas for me? Anybody got some suggestions? Things we would want to make sure are working? Yeah.
Very simple one is like ensuring that transaction IDs actually have the logs that they acquire.
Transaction IDs
And
have
keep them until they release them.
and keep them into their release. So, transactions hold locks, right? Until, man, it's hard to write like that. Hang on. Let's switch this around. Sorry. Until completion. And completion could be successful completion or an abort, right? And actually, we'd want to check both situations. So once a transaction commits, make sure all the locks are gone. Once a transaction aborts, make sure all the locks are gone, right? It should be gone either way. Make sure all the locks are gone for that particular transaction. There's a method in there called holds lock that can be used. It's basically exists specifically for unit testing, right? Does this transaction have a lock on this page? That's what that method is asking. So please use that test, use that liberally in your unit test to verify that the transactions have what locks they need to when they need to. There's a lot of other stuff we can talk about in regards to lock acquisition. Anybody have some other ideas for me? We talked about rules for locking, right? We talked about some rules for locking that we can use unit tests to verify. What are some of the rules that we have to follow when acquiring locks? Yeah. One lock for one piece of data. So I can't have multiple locks for the same transaction, right? So one transaction, I guess, might be a better way to say this. I'm trying to think of a more concise way to say it than the way I was about to say it. Oh, my computer is frozen. Number of locks. This could be per transaction, but it also could be per data item, right? There's rules on how many locks a particular data item can have out at any given time as well, correct? If I'm acquiring write locks, there can only be one. If I'm acquiring read locks, I can actually have lots. And so those are things that we'd want to try and test as well, especially as it relates to lock acquisition. So if I try to acquire a write lock, right? I should be able to do that only if there are no other locks on that piece of data. Only if there are no other locks. If I'm trying to acquire a read lock, I should be able to do that unless there's a write lock that exists. So I want to be able to test, multiple write locks, or I'm sorry, multiple read locks. But only one write lock. So think about the various combinations that you could test. I can make a transaction that acquires a read lock, make another transaction that tries to acquire a write lock, and it should fail, right? It should not acquire that write lock. I should make a transaction that acquires a read lock, and then make another transaction that acquires a read lock, and that should succeed, because that's okay. Think of the various combinations of acquiring read and write locks. Think of the various combinations that could exist. There's a lot of them. There's a lot of them. And actually, if I acquire things in the wrong way, what's going to happen? If one transaction tries to acquire a read lock and the other transaction tries to acquire a write lock, what's going to happen? If we don't use any parallel programming, we're going to hit deadlock very quickly that way. We're going to hit deadlock very, very quickly that way. And so then the question becomes, all right, can I get out of deadlock? I want to test various situations that are going to put me in deadlock, and I want to make sure that I can get out of them. Every semester that I give this assignment, somebody does not implement deadlock resolution, and then when I try to run the tests, it sits there for a very long time, and it makes me upset. Please don't be that person this semester that does that. Implement some deadlock resolution so that these tests will finish appropriately and get the right result. What should the result be after deadlock, right? What should the result be? If I have two transactions that are competing for a lock on the same data item and I detect that deadlock has occurred, correct? One of those transactions has to go, right? Something has to give. One of those transactions has to go. But one of them should survive. So in other words, blowing away both transactions, I do not consider to be an acceptable resolution here. If I were writing a test to check deadlock, I would make sure that even after deadlock occurs, one of those transactions survives and is able to continue. And it, does it matter to me which one it is? Not necessarily. The methods that we talked about in class on Monday have different outcomes in different situations. It doesn't necessarily matter which one survives. There are pros and cons to those various approaches, but at least one of those should survive the process. So definitely something to consider if you're going to be testing deadlock. All right. I'm trying to think if there's anything else related to locking that we should be testing for. I think we've covered most of the bases. We covered acquiring locks, the number of locks that can be acquired, deadlock, We talked about releasing locks when a transaction is complete. I guess something else sort of along those lines that's not necessarily lock related, but still important, is that, when a transaction completes, we should see those operations be permanent. They should be permanent operations in the file, right? So if I commit, I should check the data, which could be either an insert or a delete. And it should work. I should be able to see that the insert or the delete went through, right? If a commit happened. If I abort the transaction, I still want to check the data. The difference now is that I should see that the insert or the deletion did not go through. Those are another very simple couple sets of unit tests that would be important to have for this particular assignment. Commit means the operations went through, they're now permanent. Abort means the operations did not go through. I should not see any changes to the data from when I started. All right, let's see. Last but certainly not least, I'll touch on it real quick. Evict. I mentioned this earlier. Evict. Evict happens when my pool is full. I filled up all the possible slots, and then I want to read in one more page. I want to read in one more. So evict says that I should get rid of a page. I should kick one out. But it says that I should only kick out a page that I know is not being used by another transaction. It's a page that's old, that's been finished already, right? So properly evicting pages should work. But then there's also an edge case. There's also an edge case to consider. What if all of the pages that are loaded are currently in use? Then I don't have any candidates to evict. I have no eviction candidates, right? So no eviction candidates. What should happen in this case? I think the write-up actually talks about this a little bit, but what do you guys think? If my pool is full, I try to load a page in, but there's no candidates to be evicted, what should happen? What should I do? Should I just say, oh, well, sorry? What should I do? I mean, that's one option, right? And that's an option that I would be open to listening to. I think another option could be to throw some sort of an exception indicating that there was a problem. I tried to perform this operation, I was unable to, right? Throw an exception, make sure that whoever tried to perform that operation is aware. What would that cause? It would probably cause the transaction to abort, right? I'm not sure that we need to go that far with our tests, but that's maybe thinking a step or two ahead of what this assignment is focusing on. But that certainly is a plausible situation. Memory's full, sorry. You cannot proceed, right? Think about what you would do in that case and write a test and tell me what you want that behavior to look like. For now, we're out of time, so I'll stick around for a few minutes after if you have any questions on homework 3 or homework 4 stuff. Otherwise, get your unit tests into me by Friday at noon, and have a great weekend. I'll see you next week. What's up?
I would definitely be interested in